Christine Larson, who is a geodesist, amongst other things. She's done quite a lot of excellent work throughout her career. She received a BA from Harvard and a PhD from Scripps Institution of Oceanography. She was a professor at the University of Colorado from 1990 to 2018. She's now emeritus. She's worked on a diverse set of GPS research projects, from measuring deformations across the Nepal Himalaya to synchronizing atomic clocks and detecting seismic waves. In 2014, her research group received the Prince Sultan bin Abdulaziz Water Prize for developing GPS interferometric refractometry. Christine is a AGU Fellow and a EGU Huygens Medalist and a member of the National Academy of Sciences. So we're very pleased and honored to have her here speaking today. So Christine, over to you.
So I should click share screen?
That's right. And I will spotlight you. So you are.
And I can you see something that looks like a slide?
Yeah, I see the slides. You're not in presentation mode, but I do see the slides.
Am I in presentation mode now?
You are.
All right. So I can't see myself anymore, but that's okay. Anyway, these are beautiful GPS sites. If you're not used to them, these are the kind of sites run by geodesists. But let me just dive in. I'm going to talk for a very short time about what I mean by GPS or GNSS interferometric reflectometry. But I'm going to spend most of my time talking about the kinds of things you can measure with this technique. So I want to give you an idea of what it's being used for if you are interested in using it yourself. And then I'm going to end with some new work I've been doing. So let me start my timer so I don't go too late. So this is the cartoon. I realized too simple for you guys. Sherman told me I didn't need to go over all the details, but you know, this is my cartoon when I explain to people what geodesists use GPS for. Unlike some of your other speakers, well, I shouldn't say it that way. We're willing to spend money if it'll get us down to the millimeter. So that geodetic antenna that I'm showing here costs almost as much as the dual frequency carrier phase receiver, to be honest. And this monument I'm showing here with a tripod and a little oval there, the monument itself can be thousands of dollars because we're really trying to anchor it to the earth so we can measure crustal deformations that are very, very small. Because even though plate tectonics looks big when you look at an earthquake, it's really quite small in between earthquakes. So this is sort of the geodetic view of GNSS and GPS. We really just want to measure X, Y, and Z of this antenna phase center, period. I'm going to talk about something different, using your GPS, that same GPS system as a radar, a bistatic radar. So here I'm going to use the same equipment, the same expensive antenna, which is designed to suppress reflections. And I'm going to use that same expensive receiver. And instead of measuring XYZ, I'm going to do two things. I'm going to sense things. I apologize there. I'm going to sense things about this surface because, of course, a reflected signal is going to tell you something about the surface. And I'm also, in some cases, going to measure the distance between the antenna's phase center and that surface. That's something no geodesist cares about at all. You'll never see anybody saying, you know, my antenna is 2 meters above the parking lot if your GPS antenna is in a parking lot. But it's something that we can take advantage of when we reverse engineer these reflected signals. So that's the kind of thing I'm going to be talking about today. So this is my one slide overview of what we're doing. If you haven't thought about multipath in a while, here I'm representing only a single satellite signal where there's an antenna. Instead of using an oval, I'm kind of using a sphere here. Let's say it's 2.5 meters above some planar surface. Now that planar surface could be a parking lot, but you wouldn't be very interested in it if you were an earth scientist. But it could be soil, it could be water, it could be snow. And we could tell things about that planar surface if we looked at the reflected signal. A lot of people have done some really excellent work building instruments to measure reflected signals. I'm a geodesist. I'm going to use geodetic instruments to measure these reflections. So I don't have the luxury of designing my own instrument. I'm going to take what I have, reverse engineer it to give me something that tells me how high my antenna is above the surface, and also what kind of surface it is. Like I said, if it's wet or dry and so on. And the only measurement I have that's going to tell me that in a simple way, is by looking at the interference between the direct signal here and the reflected signal, which travels an additional distance, which I've shown in red. And sometimes that's constructed interference, sometimes it's destructive interference. But effectively, we're going to see this interference pattern, and we're going to model that interference pattern to tell us something about the surface and something about the height. And those two parameters are going to tell me something about the environment, as long as the GPS antenna is somewhere interesting to Earth scientists. So let me move on to tell you how I do that. Of course, like all of the people at this meeting that model multipath and think about reflections, I first started working on this to try and make multipath go away. Of course, there you're interested in modeling carrier phase multipath or pseudorange multipath. When I started thinking about doing this on purpose to measure environmental parameters using multipath, I knew I didn't want to use carrier phase or pseudorange data to do that. And the reason is it's hard and complicated, and it's, and I won't go into the details, but I knew from my colleagues in engineering that signal to noise ratio data could give us some of the same information, but in a way that makes it easy to use, because the direct signal no longer requires all those orbits and clocks that we've been seeing in other presentations, but it's like a polynomial. The direct signal for an SNR curve is very simple. And if we want to look at what the reflected signal is creating, it's this interference pattern. To get H, the height above the surface, we can just look at the frequency of that interference pattern. So we can look at either a rising or setting arc. If the rising arc is over someplace I'm not interested in, I can exclude it. But the same can be done for any SNR data curve for any satellite signal. This happens to be for a GPS site in Boulder, Colorado, and it's the L2C signal. Why would you want to do this? Well, to supplement in situ sensors, which are either too small in footprint size or they're expensive to maintain. A lot of people would like to measure all environmental parameters with satellites, but they don't always work so well. And some of them have very large footprints that aren't appropriate. I'm going to use geodetic data, which means by definition, somebody else has installed the instrument and they're maintaining it and they're archiving the data and they're telemetering it. So in some sense, the data are free. Those ground data are valuable for assimilation and satellite validation. The first applications of GPS-IR or GNSS-IR were terrestrial hydrology. To be honest, a lot of that was motivated by the desire of NASA to validate SMAP, a deliberate, soil moisture mission that was going to measure soil moisture. But we also started to think about how we could measure snow depth and biomass and vegetation water content. And those are valuable for climate studies, and I'll just leave it at that. So we started working on this in the mid-2000s. At the same time, the National Science Foundation funded an effort to install 1,100 GPS receivers in the Western US. So I had an idea that could be tested on a wide scale without my having to buy validation sites. I could use these science sites to validate my work and then to apply it. Now, of course, the goal was to measure deformation, and these vectors are how fast the site is moving. So the Pacific Plate here is moving 5 centimeters per year, whereas Nevada is moving at less than a centimeter. But it's the same receiver and same principles that I'll be using for my work. So I'm going to show you some examples of that effort. We were able to measure snow at about 225 sites. We included Department of Transportation sites from Minnesota just because, well, it snows in Minnesota and they were there. I'm going to show you a video because those are always fun. We were measuring snow depth at this site in Idaho. We wanted to validate it. It was expensive to send a person to measure snow depth. So instead we took a picture of this camera and then we used digital methods to, extract that number off the pole. What I'm showing here are the pictures once a week but also I'm showing you how we use the GPS data to measure snow depth. Now, all I did was take the frequency off the SNR data for all rising and setting arcs, uh, calibrate that to extract depth, and that's what's shown below. Then you can take those digital records for this camera and compare to the GPS records. And this is the kind of agreement you get. So they're very clearly measuring the same thing. Do they agree perfectly? No, nor should they. Remember, a pole is just telling you snow depth there. GPS is going to show you the snow depth everywhere reflected around that antenna over a much broader scale. We started working on this, as I said, in this time period here. By 2012, we had some preliminary results. The National Science Foundation ultimately funded us for 3 years, which was renewed, so that we were able to measure snow depth in that region for 6 years. But once you have the algorithms, the data have been archived, we could go backwards and develop climate models for over 10 years for snow. We also measured soil moisture, where here, if you're not used to soil moisture, basically it's not super complicated. It rains, soil gets wet, it dries down. What they're interested in is the interplay between temperature and whether they can use this measurement about how wet the ground is and how much water has evaporated to help them do better weather forecasting as well as climate. We did that for about 130 sites, maybe I guess it was 150 sites. This is a site in my hometown of San Diego where it never rains. You can see it only rained once in March. And you can see the soil moisture going up, and then basically we're measuring soil being very dry. My favorite site in the network is in eastern New Mexico. Here there were quite a bit more of these little storms where you can see the soil moisture going up. We also measured vegetation water content variations. This is a site north of Santa Barbara. Here we made a normalized metric, which basically we're looking at the amplitude of the multipath instead of the frequency, which gives you the height above the surface. Here we're using a little bit more of the amplitude information. The main way people study vegetation is using an optical sensor called MDVI, but basically they measure color vegetation. We measure variations in water content because GPS doesn't know what color the vegetation is. Excuse me, but you can clearly see when GPS tells you that the vegetation was in drought, where there was no growing season. And once you do that and you have a large network, you can start looking at the development of drought in California. Now, I haven't extended this to the more recent drought time periods, but if you think back, there was also a very severe drought between 2012, 13, and 14, where I'm showing basically orange are the times when California was in drought. And what's interesting to me is it was in very severe drought in 2007 as well, but that drought lasted just the 1 year. There are more details in a paper that my colleague Eric Small wrote. The next thing we used GPS for, GPS IR, was to measure sea level. This is a site in Alaska. This was the plot I showed you of how you can measure where the ground is in Boulder, Colorado. And to be honest, it's pretty boring. The ground was in the same place when the satellite was rising as it was setting, but that's the right answer. This is what it looks like when you're looking at tidal variations that are quite large. This happens to be low tide, and this is high tide. So the rising arc gives you low tide, the setting arc gives you high tide as long as it's over the water. And this happens to be a very high tidal range. You can see here on the y-axis that the tides vary here by almost 8 meters. What's shown in magenta is, quote, the real tide gauge. What's shown in blue is whenever I had sea surface reflections at that GPS site. Now, it's not continuous. This is from 2012, and I was only using L2C data at that point. And so I didn't have as many reflections as I would today. We also did long-term comparisons. The oceanography community is not really interested in tides today. They want long-term climate records. This happens to be a tide gauge shown below here in Washington State. You can see one of the problems with using other people's sensors is there are boats coming into the reflection zone of the GPS, but we basically demonstrated in this case for daily averages, better than 2 centimeter agreement. If you looked at monthly comparisons over 10 years, which is again going to be a climate scale, you can do even better. The next thing we looked at was using GPS on ice sheets. So this happens to be a study done with data collected by some seismologists in Greenland. They were setting up seismic networks. And they installed GPS instruments kind of as an afterthought. I guess they had some extra money. What they did is they buried the, it's not like an experiment where you're measuring plate tectonics. This is not a stable monument, but this pole goes about 3 meters deep, and then it's about 4 meters above the surface. Typical geodetic antenna. And it's tall because snow accumulation rates are quite large here. Why would you do this? Well, it has a relatively large footprint compared to other sensors. A typical snow sensor in Greenland has a footprint of about 1 meter by 1 meter, whereas GPS is, 50 meters by 50 meters. We can use the vertical positions to correct for snow compaction effects, relatively cheap. Again, you can use existing data sets. In this case, I can use data that was installed to measure positioning. We'll ignore that. Here are some pictures that the seismologists were nice enough to give me. I don't know if you recall in the previous photo, the monument, if you will, was flush with the snow. You can see that was installed in 2011. By 2012, there'd been so much melt in Greenland that this monument is well off the surface of the snow. But then you can see over time, sure enough, this antenna is going to be buried if they don't do something about it. And they did build them so that the antennas could be extended in length. So again, I'm going to use all the rising and setting arcs, extract the frequencies, turn that into snow depth variations, and you get something like this. Remember I talked about that big melt off? In 2012, you see almost 1 meter of melt in the summer. A more typical melt off would be like here in 2015, where it'd only be about 20 centimeters. So this was a really large effort, but you can also see that this particular site has a lot of snow accumulation. So I want to talk a little bit about new things. Looks like I'm going to finish on time, so that's good. I think we've moved a little bit from using other people's sensors to actually doing what I'll call deliberate GNSS-IR. Soil moisture, snow depth, Greenland, tides. I've always been using geodetic sensors that happen to be close enough to the water that I could do something with them. But the results from Antarctica and Greenland were so compelling that people are now putting these sites out on purpose. So that means that, sure, it gives you positioning, but there's a GPS antenna at the top of this 30-meter tower, because they really, if they're going to measure snow accumulation there, they don't want it over a 1 meter by 1 meter footprint. They want it over a larger footprint. And this gives them that. These are 2 other sites in Antarctica. The other thing I've been doing is when I see something in the news, to be honest, I sometimes ask myself if I could measure that. This happens to be motivated by Hurricane Laura. I guess they call it a level 4 hurricane. It crossed the Louisiana coast, basically on top of a GPS antenna that was operated by Louisiana State University. So this is the eye of the hurricane, and the cyan star there is the GPS antenna. Now, Louisiana State put it on top of this tide gauge that is maintained on a I don't know what you call it. They call it a sentinel, but in any case, it's in a canal that goes from the ocean to one of the interior lakes in Louisiana. So to be honest, measuring water levels with this data set is pretty easy because this one is in the water. And what's shown in blue are just the GPS reflections, because those are the ones I do in real time. What's shown in blue is the actual tide gauge that NOAA operates there. And then what's shown in red is wind speed. So you can see that this, in fact, these are metric units. So this is almost 100 miles per hour. Now, definitely GPS reflections doesn't work when the sea surface is too rough, but what you can see happens is as that eye crossed the coast and went over this GPS receiver, the wind speeds died down because the eye, then they went back up. But you can see that when the eye was over the site, GPS reflections could measure that sea surface again because it was smooth enough. Basically above 30 meters per second, we couldn't do anything, but below that, we were able to measure sea surface through a magnitude, I call it magnitude, I guess they would say a level 4 hurricane. This is a real shout out to the people that built that antenna and receiver as well, that the GPS instrument lost no data whatsoever during this hurricane. The other thing I've been doing is looking at tsunami signals. Again, this was kind of motivated by the news. There was a magnitude 7.8 earthquake in the Shumiga Islands in Alaska this summer. It did not create a huge tsunami, to be honest. It was only about plus or minus 30 centimeters. But there was this GPS site that had been put in by geodesists. It was 70 meters above sea level, but we're able to see the sea surface. So we could measure tides. These are tides measured by that site. This is the GPS data being used to measure the earthquake. It caused the earth to move 33 centimeters up in about 20 seconds. What's shown here in the colors are my retrievals of sea surface during that tsunami. I just color coded them by whether they're rising or setting arcs. Now it's not continuous, but that's because this only tracks GPS signals. This site has not been upgraded since 2007. I think it's pretty obvious that if we want to use this kind of system for warnings for tsunamis and hurricanes, it needs to be GNSS. We need the Galileo, Beidou, and GLONASS signals so that we can get better temporal variation and we can fill in all these empty spots, basically. So I guess I wanted to say a little bit about users, maybe make a plug for getting people at this talk interested in this. There are three kinds of GNSS IR users I've decided. The first category is people that really don't want to know anything. They want you to give them a text file with the answers in the file, maybe an Excel spreadsheet. Anyway, they really don't want to know anything about it. Just give me the numbers. And so that takes some effort to come up with a system that can work for those people. And so for fun, really, I made a web app that does that. It's basically GNSS IR on demand. You can either upload your own data file and it will tell you how much snow is on the ground or what sea level is. There's some examples that have been set up to show you what a good site is. And it also, you can say, look, I know a station, I know the data are archived, and you can input that information as well. So this is sort of for the environmental scientists who don't want to know the details. There are people, of course, like the people that are listening here that are willing to install code and learn how it is used. I have to say in general, geodesists aren't interested in measuring environmental signals. It's hard to get them excited about it. They're used to measuring plate motions. They're used to measuring earthquakes, volcanoes. That's all pretty exciting to them. So I'm working at it, but I wouldn't say that I've succeeded yet, but I have made an open source Python package available to try and get people working in this field. It certainly helps environmental scientists if more of us are making codes available to the broader community. And then the third category is really the experts. And I think this community here, because you know the multipath equations, because you know how radars work, and you know how these high precision models are implemented, I think that you could make a contribution if you're interested. So here is my plug. If you're interested, please let me know either by emailing me or looking at what I've put out there and get involved. And I think that's it. That's my last slide.
Thank you, Christine. That's very, very interesting work. And I love the 3 things you offer at the end there to make it available publicly for people who want to do this at different levels. And it's really nice the fact that you can go backwards in time, as you say, as you develop this process, and you can go back and look at old data without
I
having
think
to.
that's one thing.
Go ahead.
I mean, I don't know if anybody's going to ask this, but typically when I talk to engineers, they always want to build their own instrument. And the question is always, can't I build this cheaper? And can I build a better sensor? And the answer is, of course you can. If you're going to build something to measure multipath, I would like to think you could do better than the people that spent $5,000 to not measure it, right? I mean, those geodetic antennas themselves are $3,000. But the question is always, can you use what Sherman's talking about? Are you going to telemeter your own data? Are you going to archive your own data? Are you going to have 10 years of data sitting in an archive ready to be used immediately? And the answer is no. So I would encourage you to build those cheaper, more accurate reflectometry sensors, but just keep in mind, you're going to have to operate those sensors too, and you're going to have to archive them, the data, and so on. So there's some value in doing both. I really get excited when people do use the cheaper sensors, but there has to be a balance because these sites have to be maintained. And I said that I didn't install my own sites, but of course I lied. I installed sites because I had to validate my work, and I had one of my sites was vandalized by people that opened the equipment box and left it open, you know, in 0-degree weather. And another one that had a fire, it was burnt. I had other sites that were, all the wires were eaten by mice. I've had, you know, I mean, if you maintain your own instruments, it's not a zero cost. That would be my comment.
Yes. I think we have time for a question here. We'll go ahead and let Christoph Günther is wants to ask the question.
Yes, thank you very much, Christine. It was a very nice talk. And it's very clever. And I'm wondering one thing, because you were saying you don't want to mess around with carrier phases and so on. My impression is that this is exactly what you're doing. You're doing an interference between the direct path and the reflected path. And as the satellite moves, the carrier phases are shifted with respect to each other. And that's what you're measuring. And so I think you're doing it, but you're doing it in a very clever way. You're doing an analog processing of it.
I mean, the thing is, actually, I spent 5 years modeling carrier phase multipath. So I just meant that when you start thinking about carrier phase observables, you can't just ignore the things that are going on in those observables. Of course, you should you have to think about clocks and orbits and so on. The nice thing about this method is that by using SNR data, I really don't have to think about it as much. But yes, of course, you're absolutely right. I am at some level doing exactly what you're saying, but I usually don't tell people that because, you know, you show people SNR data, they can see the frequencies, they can see what's going on. Sure. It's kind of a nice.
But the modulation is due to this interference.
Yes, absolutely. It's the same principle. Absolutely. Absolutely. And I actually did fib a little bit. The vegetation statistics are based on pseudo-range multipath, to be honest with you. So we've done both, but the soil moisture, sea level, all of that is based on SNR data that are collected by geodetic receivers.
Excellent.
Yeah.
We do have a question here in the panel, which is the GNSS antennas normally reject signals below the horizon, and asking about the design of the antennas for receiving reflections from below the antenna's horizing. I believe what you said
below 0 degrees.
Ones, right?
I'm not. Are you talking about low elevation or just below 0?
Well, you're using the geodetic ones, and I think you mentioned, right, they're designed like a choke ring to reduce the reflections, but they don't eliminate them, and you're you know.
Yeah, I mean, I didn't understand antennas nearly as well as I thought I did until I worked on this for 10 years. They don't reject multipath below 15 degrees elevation angle. I mean, that's just an urban legend. They do a really good job of above 15 degrees, but for natural surfaces like soil, water and snow, it's trivial to see these multipath effects. Now put them, ironically, if you put that expensive choke ring on a large metal roof, there'd be no reflections. Believe me, because I've purchased large amounts of metal and put them under an antenna. I mean, we actually did some of these experiments to convince ourselves that we knew what we were doing. And those antennas, you still can see enough right-handed energy from that reflection, which you wouldn't see if you had a metal surface. People ask me whether they should keep using choke rings, and I say, sure, there's some value, a lot of value to choke rings, but they don't reject multipath from natural surfaces below 15 degrees elevation angle. They just don't.
And for Antarctica or for future ones, would you want to change the antenna, or you feel there's no need to change the antenna based on what you've seen?
I think because the value of the geodesy and the reflections, you should use a cheaper geodetic antenna. There's no reason to spend $3,000 on a geodetic antenna if you're going to use it for reflections and there's a calibration for the phase center variations of your choice. I've used lots of different ground planes. As long as you have those anechoic chamber measurements of the phase center variations, you should go with the cheaper geodetic antenna, I think, and go for it. I don't see the reason to have a choke ring in Antarctica myself. That's what I tell people. But there are other reasons to have a choke ring. And one of it is conformity. Geodesists are the most anal conformists you'll ever meet. They want every single antenna in the world to be a choke ring, and that's fine for them. But if you're down in Antarctica, that's not the community using those instruments. It's people, there are other reasons to make those measurements.
Okay, great. Well, thank you very much. Very much appreciate
Okay.
your talk. We'll go ahead and we'll take a break now, and I think we will start at back in 10 minutes. So we'll start at 10 a.m. Pacific time, and we'll do